Farmers use fertilizers to increase the nitrogen content of the soil and improve crop production. One of the chemicals they use is ammonium nitrate. The starting materials are ammonia gas and nitric acid. Ammonia is made industrially from nitrogen and hydrogen. The two gases are mixed in a pressurized container. This is the equation for the reaction. Each nitrogen molecule reacts with 3 hydrogen molecules to form 2 molecules of ammonia. But once the ammonia has formed, it can also decompose back to nitrogen and hydrogen. The reaction is reversible. It can go forwards and backwards. In industry, the reaction takes place in a pressurized tower and in the presence of an iron catalyst. It's called the Haber-Bosch process. A temperature of 450 Celsius and a pressure 200 times greater than atmospheric pressure are carefully chosen to maximize production. Ammonia is the starting point for making ammonium nitrate. The other raw material is nitric acid. To make nitric acid industrially, ammonia gas is oxidized in a huge burner. Ammonia reacts with oxygen in the air to produce nitrogen monoxide and water. For the reaction to happen at a reasonable rate, it needs a platinum catalyst. See how a hot platinum wire glows when it's suspended above a solution of ammonia. It's a sign that ammonia vapor and oxygen are reacting. The same glow happens inside the industrial burner. In industry, the catalyst is a very expensive sheet of platinum gauze. The next step is for the nitrogen monoxide to be oxidized further. Nitrogen monoxide reacts with more oxygen to produce nitrogen dioxide. Add air to a flask of colourless nitrogen monoxide gas, and it forms brown nitrogen dioxide. To produce nitric acid, the final step involves reacting nitrogen dioxide with water. This is the equation for the reaction. So, when the flask contains nitrogen dioxide and water, the brown gas disappears. It dissolves to form a clear solution of nitric acid. Finally, ammonium nitrate is made by adding nitric acid to ammonia solution. As the acid is added from the funnel on the left, a reaction occurs immediately, forming a cloud of white ammonium nitrate. Today, we rely on plastics to make all sorts of objects. But the raw material for all these plastics started life millions of years ago. They're made from crude oil. Before it can be used in the plastics industry, it has to be processed. A key reaction that happens at the refinery is called cracking. Cracking is where long-chain molecules in the oil are broken down into shorter ones. To get an idea of what's happening in these towers, we can crack a fraction of crude oil in the lab. This is liquid paraffin. It's just one of the chemicals refined from oil. Paraffin molecules are chains of 20 or more carbon atoms, joined together by single bonds. Hydrogen atoms are attached to each carbon atom. Molecules like this are known as alkanes. All the carbons are joined by single bonds. To crack the paraffin, a small amount is dropped onto a piece of glass wool. It's heated in the presence of a ceramic catalyst. To begin with, heat causes air inside the apparatus to expand, so the air bubbles out. After a few minutes, the paraffin is heated and it starts to decompose. The product is a colourless gas and it's collected over water. Each paraffin molecule has now been cracked or broken down into two shorter chains. One of them contains a carbon-carbon double bond. This type of molecule is called an alkene. Once a full tube of gas has been collected, it's sealed, ready for testing. Bromine water is used to show that an alkene is now present. If the gas in the tube contains molecules with double bonds, the bromine reacts and loses its colour. Molecules containing double bonds are the basic building blocks for a group of plastics known as polymers. Each building block is called a monomer. Thousands join together to form long chains called polymers. One of the most common polymers in use today is polystyrene. It starts life as the monomer styrene, a runny, clear liquid that looks and behaves like water. This is the chemical structure of styrene. It forms a polymer by opening up its double bond. The end of one monomer bonds to the end of another, and so on. This is called polymerization. At room temperature, styrene polymerizes fairly slowly. To increase the rate, a small amount of initiator is added, and the styrene is immersed in a water bath. After an hour, the consistency has changed. It's getting thicker. Leave it for another hour, and the styrene is even thicker. It's forming polystyrene. Eventually, it'll be a rigid plastic. In industry, the starting materials are mixed and heated in large sealed tanks. Additives make the product more rigid and change it from clear to white. It ends up as tiny pellets of polystyrene, ready to be melted and moulded into all sorts of shapes. This is pure sulfur. It's been extracted from rocks in the Earth's crust. When sulphur is heated over a gentle flame, it melts to form a runny yellow liquid. Heated more strongly, the sulphur darkens and becomes much more viscous. When sulphur is heated in air, it burns. Sulphur reacts with the oxygen in this gas jar to produce a characteristic blue flame. The white fumes left behind are sulphur dioxide. This reaction is the starting point for making sulphuric acid. Liquid sulphur arrives at the sulphuric acid factory in a huge tanker. It's sprayed into a furnace and burnt in a blast of dry air. Sulphur combines with oxygen in the air to form sulphur dioxide. As the sulphur dioxide leaves the furnace, it travels to the converter, where it reacts with even more oxygen. A high temperature of 450 Celsius and a vanadium pentoxide catalyst speed up the reaction. Sulphur dioxide and oxygen are converted into sulphur trioxide. But as the temperature rises, the sulphur trioxide tends to break back down into sulphur dioxide and oxygen. Unfortunately, it's a reversible reaction. It can go forwards and backwards. So at the production plant, they make sure that the reactor doesn't get too hot. In the final step, sulphur trioxide gas flows into the bottom of an absorbing tower. Here it meets a solution of ready-made sulphuric acid. The sulphur trioxide reacts with the water in the solution to produce even more sulphuric acid. Sulphuric acid has many uses in industry. An important property is its ability to absorb water. Here, concentrated sulphuric acid is added to ordinary sugar. The acid acts as a dehydrating agent. It removes water from the sugar molecules, leaving only carbon behind. The water escapes as steam.